phi and arm is right in the arm shell.
Oh, yeah. Sorry, where? What?
Yeah,
On the far right.
Yeah, sorry.
There
Yeah.
might be half also, half there.
You think there's a half?
Yeah. No half. It's a real scalar to differentiate the.
Oh, sorry. Yeah. I mean, the action itself.
Yeah, half there.
Yeah, there's a half somewhere. Where's the half go? You
Half
think
there.
it goes here, right?
That's right, yeah.
Yeah. Okay, thanks. Okay. What we're going to do is we're going to use this to derive the conformal transformation law of T mu nu. But what I want to do first is calculate the one-point function T of z in conformal gauge, but in a general metric in conformal gauge, general background. Okay, that thing. I'm going to calculate this one-point function. And then we're going to use the relationship between vial and conformal to read off the conformal transformation of the stress tensor. Okay, so this one-point function we can get just by differentiating. I could probably just write down the answer, but I think it's kind of instructive to go through this. So this is 4 pi over root g delta g z z of minus sp. And the variation of sp, sorry, sp is the Polyakov anomaly action there. So the variation of sp is, of course, just the usual stress tensor. Okay, so when you vary an action, you get root g times the stress tensor for that action, delta g mu nu. That's pretty much the definition of the stress tensor. But now, this is not the stress tensor of the CFT. This is the stress tensor of the Liouville action. So what T phi means here is it's the stress tensor associated to that action, as if you just pretend that's a scalar field action. So it's C over 24 pi. I won't go through the variation, but this is what you get: a half d mu phi minus grad nu phi plus g mu nu del squared phi minus 1/4 del phi squared. Okay, so now we're supposed to set box phi equal to R. Okay, so box phi is equal to R. I just noticed I made an error. I hope it doesn't matter. So when I was working this out, I wrote that that's minus 2 box rho, but I think this is missing a root g. The root g is going to give us a extra factor.
You remembered the root g last time.
Yeah, I did remember the root g last time, but I did not include it when I was working out the calculation I'm about to do, and I still got the right answer. So let me just proceed. And however, I'm going to have to double check this, and it's possible that it either drops out or I somehow canceled the error.
it'll probably cancel with G mu nu, right?
It probably cancels with G mu nu.
Yeah, G mu nu has a e to the 2.
Yeah. Ah.
Yeah, I think.
Yeah. Yeah. Okay. So I think it's gonna. I think the next equation is just gonna be good. So. So now we can calculate the stress tensor T in this metric, which remember is minus 2 pi times the expectation value of TZZ in this metric. So this is what I plugged in when I did this at home, but I think I missed this factor of e to the, I think I missed the e to the rho. But I guess it must cancel when we put it in because it still works. And what you get when you plug it in is actually really simple because in TZZ, GZZ is 0, so that term just drops out. So it's pretty easy to calculate this, and you just get C over 6 times 0 squared minus d squared rho. Let's do an example. So everyone's favorite conformal transformation, and yeah.
In the stress tensor,
Yeah.
I'm varying with respect to the metric.
Yeah.
Shouldn't I have something that looks like the Einstein tensor for keeping phi fixed and varying r?
Einstein tensor vanishes in 2 dimensions.
Yes. Thank you.
Oh, that's why.
Yeah.
Okay.
Okay, let's use this to calculate the stress tensor on the cylinder. So the metric on the cylinder is 1 over mod z squared bz bar. So let me remind you why that is. It's because if we set z equals e to the iw, then set w equal to phi plus I tau, then this ds squared cylinder becomes just dw bar, which is d tau squared plus d phi squared. And furthermore, the fact that z, this coordinate change tells you that w is periodic mod 2 pi. Okay, if w is periodic mod 2 pi, that means phi is periodic mod 2 pi, so phi is really an angular coordinate, and this is really the cylinder. Note that I am not doing a conformal transformation right now. I'm just doing a coordinate change. It's a coordinate change, not a conformal transformation at this point. So this prefactor is e to the minus 2 rho, which means that the cylinder has rho equal to minus a half log zz bar. So we plug that in, and we find T of z in the metric 1 over mod z squared bz bar is So you just have to plug this rho into that formula there, and you'll get minus c over 24z squared. Which means that now we're going to do a coordinate change to go to the w coordinate. Okay, so t of w, and this notation is kind of annoying, but this everyone does, I can't help it. So t of w, this means minus 2 pi tww. It is not the same function, because of the indices on t, this is not the same function t of z evaluated in w. Okay, but that's how we do. Okay, so t of w in the cylinder metric, which is dw bar, w identified mod 2 pi. Is just given by a coordinate change. So this is the usual tensor transformation, dz dw, dz dw, t of z in the same cylinder metric. So z is e to the iw, so this is just a factor of z. Each of these is a factor of z, and we get c over 24. Each of those is a factor of ic. And we get c over 24. Okay, so that's the stress tensor on the cylinder. I want to now infer from that the change in the charges. So the charges associated to translations in the w direction, dw. So this is going to be the integral of tww on the cylinder. And we said that so T is non-zero in vacuum on the cylinder, which means that you're going to get a shift as compared to so L0, the Virasoro generator, this was defined to be this conformal generator on the plane, which is the integral of T on the plane. But we just determined that T on the plane and T on the cylinder differ by a shift. So the charges are gonna come in with a shift. The same thing holds for dw bar. This is L0 bar minus C over 24. The Hamiltonian H on the cylinder is the charge associated to time translations, dd tau. And so that's the sum of these. It's the sum of these two. So it's L0 plus L0 bar minus C over 12, which is the dilatation generator D minus C over 12. that means that conformal dimensions, scaling dimensions, which are eigenvalues of D on the plane, give you energies on the cylinder up to this shift by C over 12. It also means that the cylinder vacuum has a non-zero Casimir energy. It has E vac is equal to minus C over 12. Let me draw a picture to explain what this means in radial quantization. So on the plane, we can do the path integral on the unit disk, and that defines for you the vacuum state in radial quantization. So this is on the z-plane. In the w coordinate, you have a cylinder, and you can define the vacuum state on the cylinder by, I guess I should only do the path integral over half the cylinder. Okay, so you define the vacuum state on the cylinder by doing this path integral over half the cylinder. And so in the state, remember there's a correspondence between operators and states. And the state operator correspondence that's going on here is that the identity operator can be, the nothing, just nothing. The identity operator does nothing. So if we insert the identity operator, this defines the vacuum state on the plane. And that corresponds to the vacuum state on the cylinder. Now the identity operator has scaling dimension 0. And under this shift, the dilatation gets shifted by minus C over 12. So the energy on the cylinder is minus C over 12.
Tom,
Yeah.
is there any negative sign in your convention where you go from the stress tensor to the charges? Because can't I think of this as the energy density?
Which one?
The expectation value of stress tensor in vacuum, in the cylinder vacuum.
Yes, it is. It's an energy. Well, it's TZZ, which is more like an energy. Yeah, it's like an energy density. The energy density would be T00.
Yeah.
Yeah.
So, when you translate that to energy, there's some change of sign.
Yeah, that's built into these conventions.
Okay.
Yeah. Okay, so now we can finish the derivation of the conformal transformation law. So recall that special Weil transformations can be reinterpreted as conformal transformations. For scalars, let me remind you what the relationship is. It says that O of x in the metric omega squared dx squared with omega, the determinant of dx prime dx to the 1 over d is equal to O prime of x prime dot 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 in the metric dx squared. I don't think I wrote this in quite this way before, but I think this is the nicest way to think about it for these purposes. So let me put a box around it. I wrote it for the scale transformation, but I don't think I wrote down the general one. O prime of x prime here is the conformal transformation. Okay, so this is telling you how conformal transformations are related to these special vials where the vial factor is pure diff. So we're going to use this transformation. We need to do it for a spinning operator because we're doing the stress tensor. For the stress tensor, we already calculated the left-hand side because we calculated the expectation value of the stress tensor in the curved background. So we're going to use that to read off the right-hand side, which is the conformal transformation of the stress tensor. So for our case, we have coordinates z and w. So you should think of w as being the primed coordinate. And so omega squared is e to the 2 rho is dz prime dz. So that's, in this case, dw dz, dw bar dz bar. So rho is therefore a half log of w prime of z, w bar prime of z bar. So what we just calculated a minute ago was this thing, the stress tensor in a vial transform background, and we got c over 6 d rho squared minus d squared rho. So now you could just plug in this particular row here for a general conformal transform, the row corresponding to a conformal transformation, and find T of z. And what you find is that this gives you what's called the Schwartzian derivative. Well, minus c over 12 times the Schwartzian derivative, w comma z, which I'm about to define. Definition of this brackety brace thing, the Schwartzian derivative, is f triple prime over f prime minus 3/2 f double prime squared over f prime squared. So it's sort of a mess, but that's just what you get when you plug in that row into the Liouville stress tensor. so over there, I wrote the relationship between vial and conformal for scalars. I'm going to write it down for the stress tensor. It just says dw dz squared times the expectation value of t of z in the metric dw squared is equal to t prime of w dot 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 in the metric dz squared. So that should be mod dw squared mod dz squared. And w is z prime. So the only difference from the scalar one that we discussed before is that we also have to stick in this factor for the indices. Sorry, that's upside down. Wait. Yeah, that's upside down. That should be -2. Because this has 2 lower z indices, and this has 2 lower w indices. So it goes that way. Okay, so we've done it. We've calculated the we've calculated the left-hand side, and so we can read off the conformal transformation of the right-hand side. I did this for the 1-point function with the stress tensor just by itself, but if you have other stuff in there, it really just comes along for the ride. So we can get the whole answer this way. And we get the transformation law. T prime of w for w equals c prime is dw dz to the -2 times t of z minus c over 12 times the Schwartzian derivative w comma z. Yeah.
I'm a little confused about the statement of vial versus conformal. Isn't it true that we're just doing conformal transformation and going to the right-hand side? And that's like a certain vial transformation? Is that what that is?
The statement is that these special vial transformations can be also interpreted as conformal transformations. And yeah, that's the statement. So we're doing this on the two sides. We're doing the same thing, but on one side we're interpreting it as a conformal transformation. The other side we're interpreting it as a vial transformation.
A vial transformation that corresponds to like a change of coordinates.
Well, I mean, yes. Well, vial transformations change the metric, but then you can, if it's one of these special vial transformations, you can then undo that change in metric to reinterpret it as a conformal transformation. It's like if you have, say your metric is, say your metric is dx squared. Okay. Well, if I do this vial transformation, I have changed the metric. This is a new metric. Distances are bigger than they were before. This is truly a new metric. However, I can absorb it into the x coordinate, call that x prime, and so it hasn't changed the manifold. It hasn't changed its structure as a Riemannian manifold is really the same. We've just relabeled things. So if you kind of undo that, then you can relate the vial to the conformal. This is really, so let me write the other. Okay, there's two ways to write conformal invariance. One is this. Conformal invariance, and note that it's O prime, O is changed as O of Z, O prime of Z. This is one way to write conformal invariance. And the other way to write conformal invariance, it's just a rewriting of this equation, is that equation that we had there. It's just another way of writing conformal invariance, where on one side you do this rescaling on the metric, so that you can reinterpret it as a vial transformation. It's not totally trivial to go from this one to that one. It's kind of a little painful, but
So you've done some conformal transformation on the coordinates, but it doesn't change the metric because you absorb it back into the new coordinate, is what you're saying.
yeah. In equations like this, okay, let me keep explaining. Okay. So sometimes people write equations for O prime of Z, and other times they write equations for O prime of Z prime. And you can write your transformation law either way. But of course, the right-hand side of these equations will differ. Okay, so you have to be sort of careful in how you read various sources. The way this one is written, it's like T prime of Z prime. So I'm writing T prime of Z prime. In particular, if you replace O of Z by O prime of Z, physics is invariant. That's the statement of conformal invariance. If you replace O prime of Z by O prime of Z prime, the physics is not invariant. The correlation functions will change. You'll get a different answer. Like if you plug this in, if you do this inside a correlation function, you'll now get a different correlation function. But the interpretation is that this is the physics in the vial transformed metric. So let's look at the stress tensor. If you take some correlators, T of Z, and you just replace them by T prime of Z inside the correlator, then you get the same answer as before. But if you replace them by T prime of W, then you learn about physics on the cylinder. The other thing about, where is that equation? Yeah, this equation here. Okay, note that you can either talk about correlators on the cylinder, which is the dW squared metric, or you could talk about operators on the plane that act like they're on the cylinder. See, T prime of W prime is supposed to be, it's an operator that we then evaluate in the theory on the plane. So for most of the literature on two-dimensional conformal field theory, we never actually change the metric.
Do you mean T prime of W?
Z prime, the W is Z prime.
Okay.
Yeah. So for most of two-dimensional conformal field theory, we never change the metric. We just change the operators. But when you change the operators from T of Z to T prime of Z prime, you learn about the physics on the other metric. This is extremely confusing. Like all of the literature, you have to unpack what they're saying. But usually this is what they're doing. Usually in two-dimensional conformal field theory, when people say they're going to do a conformal transformation, they mean they're going to take T of Z and map it to T prime of Z prime, and use that to learn about the physics in a different metric without actually changing the metric. Does that make sense?
Can you repeat that?
Okay.
Just that last sentence.
Let me say it a little bit differently. Say we want to learn about the one-point function on the cylinder. Our goal in life is to learn the one-point function of the stress tensor on the cylinder. Okay. We can either go through this procedure of Weyl transformations like we just did. That is not how people do it in real life. What they do is they write down this transformation law, and they evaluate the right-hand side on the plane. Because this is T of Z. This is something that you evaluate in the theory on the plane. You take this thing, you evaluate it in the theory on the plane. On the plane, that one-point function of stress tensor vanishes. So when you evaluate this on the plane, the first term drops out, and you get a constant, which is the C over 24 expectation value of the one-point function. But T of W on the cylinder is equal to this on the plane. That make sense?
That's because you put a W there and not a C. Cylinder.
You mean here?
Yeah, right.
I'm not sure what you mean by that's because. If I.
Meaning that's like the distinction that you were making before about whether you put a Z or Z prime.
It's because we put a Z prime here.
Yes.
It's because this is a Z prime.
You
That's
also need to put a Z prime.
right. If we had calculated this, T prime of Z on the plane, then we would get 0, because by conformal invariance, this is the same as T of Z on the plane.
That's confusing.
It's extremely confusing.
That's confusing because this seems to say that T prime is just 0 everywhere. How could it not be 0 if I just put a different, if I evaluated it at a different point?
No, its expectation value is 0. It's not 0 as an operator.
Okay, but it wasn't 0. Its expectation value wasn't 0 when you evaluated it at W, right?
I see what you're saying. Sorry. Okay, now you've gotten me confused. I told you it was confusing. Yeah, I guess this is not 0. this is not zero. Let's see, so. Yeah, I guess the problem is that what I was writing is true for primaries, but T is not a primary. So it's not zero. I mean, usually people kind of just sweep this under the rug, but the reason I'm emphasizing it is two things. First of all, it makes the old books and stuff really confusing because people are always talking about CFT, especially in 2 dimensions. They're always talking about CFTs on different metrics, but usually they don't change the metric. Like they talk about the CFT on the plane and then on the cylinder, but they're always using the same. They're not changing the metric at any point. They're just changing the operators that they're using. You can interpret it as changing the metric, but when people write correlation functions, in 2D CFT, they never write what metric they're using down here. And the reason for that is they're always using the flat metric. They're always using the metric on the plane.
So what answer would we get for that?
For what?
Expectation weight of T prime Z in the plane. I mean, are T prime Z and T prime W just related by, I mean, Taylor expanding Z?
Yeah, exactly.
Okay.
Yeah. I don't even know if there's a nice formula for it. You could certainly do it like out to linear order, and that's the infinitesimal conformal transformation. I'm not sure what the nonlinear formula is. There's some equivalent ways of writing this transformation law. One is to write it infinitesimally. So the infinitesimal transformation of T is minus 2T d epsilon minus epsilon dt minus C over 12 d cubed epsilon. I'm not really going to use this one, I don't think, but I just thought I'd write it. It's just the infinitesimal version. I think if you look like in the Simmons stuff and notes, he actually derives this one first, and then exponentiates it to get to the other one, so that'll work. Another way, these are all equivalent. Another way you can write this is by writing the OPE. So the OPE just means you bring these operators nearby and expand out. So the OPE is C over 2 z to the 4th plus 2 t, sorry, that was the z minus w 4th. Two t of w over z minus w squared plus dt of w over z plus less singular terms. Okay, why does this have anything to do with conformal transformations? Well, the reason, and we'll see an example of this, but the reason is that the way to do a conformal transformation is to act on T with a conformal charge, like Q of epsilon acting on T of W will tell you how T transforms under a conformal transformation. And Q itself is made of an integral of the stress tensor. So when you do this integral, the non-zero contributions to the commutator will come from the singularities in the integral, and therefore it'll come from the short distance behavior of T with T. The third equivalent way of writing this is as an algebra. This is the Virasoro algebra. And I don't think I'm really going to use this in this class either, but I just wanted to put it up there for completeness. These are all equivalent. These are all equivalent. You can talk about the conformal transformation of T, the finite one, the infinitesimal one, the short distance behavior of T with itself, or the algebra of the charges, which again is going to come from the short distance behavior of the two T's hitting each other. So all these things are just equivalent ways of describing conformal transformations of the stress tensor in 2 dimensions. Sorry?
Z minus W?
Yeah.
Oh, yeah.
Yeah, thank you. I just realized why I made that error a minute ago, so maybe I should tell you, because this is useful. Okay, so T of Z on the plane. Let's do this is 0. T of Z on the plane is 0. So let's do a conformal transformation. And let me make my wrong statement again, and then we can break down where I went wrong. Okay, so I said by conformal transformation, this is equal to T prime of Z on the plane, which is therefore 0. My error was in the fact that the vacuum itself is not conformally invariant in 2 dimensions. Okay, so how do you get from here to here? You act with a conformal transformation. So this is really 0, U, T of Z, U inverse. So acting with a conformal transformation takes you to here, which in higher dimensions, the conformal transformation is trivial on vacuum, because the vacuum is conformally invariant. But in 2 dimensions, the vacuum is not conformally invariant.
If it were one of the global conformal transformations,
then it would work.
then it would work.
And the Schwarzian derivative vanishes on the global transformations, so it does work. But yeah, so the true statement is that 0, 0 on the plane is equal to 0 prime, 0 prime. That's true. These 2 things are equal. But 0 prime is not the vacuum state. It's whatever you get by acting with this conformal transformation on the vacuum state. That was the where I messed up. Yeah.
Can we also understand it in a way that because this mapping, this transformation is z equals exponential IW.
Yeah.
And the geometry changes, like it's no longer a plane, it becomes a cylinder. Like the W coordinate is not.
Right.
One
But
dimension is compact, so you cannot really evaluate it on the plane on the right hand side.
You're saying it doesn't even make sense to write T prime of Z because it's not a function of the right thing? Is that what you're saying?
T prime of Z makes sense, but T prime of Z on the plane, maybe that's because the geometry really is a cylinder in a W coordinate, in U coordinate.
No, I think you can. I think you really can do this. I mean, I don't see why I can't act with. I can take a charge and I can exponentiate it. So if we write this in operator language, all I've written here is 0, T of Z 0. And this is all going to happen in one theory. It's going to be the theory on the plane. Within this theory, I can write 0, e to the minus q, e to the q, T of Z, e to the minus q, e to the q 0 in this theory on the plane. This is, by definition, T prime of Z. And this is what I was calling 0 prime, which in higher dimensions would just be 0, but here it's not. So I think it does make sense to write it.
I have another question.
Yeah.
So you wrote like the same state 0 prime on both sides of that expectation value.
Yeah.
But I thought we saw before that these U's are not unitary. In which case U inverse is not U dagger, and the two zeros get transformed into the same thing. One of them.
Yeah, I'm not sure they're conjugates of each other. I agree with that.
Okay.
Yeah, they're probably not conjugates of each other. Yeah.
And that's weird. That means that like it's not really an expectation value anymore.
True. Yes. Yeah. Okay. I have just a couple more things that I want to cover in 2D CFT, and then we're going to get out of this bog and go back to like quantum information and black holes. I promise I'm going to write up some notes with all these primes in them because they're really a real
Every time I
pain.
relearn this, I have to like
They're such a pain.
Can we also
make sure I understand it.
Can we also go over the homework problems at some point, or at least like selected things from the homework problem?
Yeah, maybe. Yeah, let's look at after and maybe. I don't know. Do other people want to go over the homework problems? I guess we can. Let me see. Let me think about it. Yeah.
Tom, do you know a good reference to like clearly states of the difference?
No, that's the and part of the problem is that the notation is terrible. And I've started writing some notes on this, and I've found it basically impossible to find good notation, and it's driving me crazy. And that's why it's so confusing. But I'm going to keep trying. I mean, everyone gets the right answer. Like everyone, that's the most annoying thing is that like there's this art to putting the primes in the right places, and everyone gets the right answer. But I can't quite find like the best way of saying it in a way that's totally clear and unambiguous and everything. Okay, so primaries in higher dimensions were eigenvectors of the dilatation operator. In 2 dimensions, you really can, for most purposes, you can think of the dilatations acting separately on Z and Z bar. So you have your L0 eigenvalues and your L eigenvalues. Those eigenvalues are called H and H bar. And so the scaling dimension delta is H plus H bar, because that's L0 plus L0 bar. And the spin is H minus H bar, because if you take because L0 minus L0 bar corresponds to the vector field dz minus d bar dz bar, which is the rotation on the complex plane. I call this the spin. It's really the helicity, because it can be positive or negative. Its magnitude is the spin, but people call it the spin, so I'm going to call it the spin. the conformal transformation is O prime of ZZ bar is dz VZ prime minus H dz bar prime minus H bar O of Z prime Z bar prime. An important point is that this is the transformation law for a primary of weights H comma H bar. Important point is that the stress tensor is not primary. Okay, this is simple. The stress tensor had this crazy Schwartzian derivative. It was just like this plus the Schwartzian derivative. Okay, so T mu nu is not primary. It is what's called quasi-primary. So quasi-primary means that it's primary under SO22, the subgroup of the conformal group, which is generated by L0 plus minus 1 and L0 bar plus minus 1. That's the piece that's similar to higher dimensions. So in higher dimensions, the stress tensor is primary, but in 2 dimensions, it's only quasi-primary. Was there a question, Elliot?
I think I understand it now.
All right. The last little bit of CFT technology that I'm going to need is the word identity, and a couple of examples we'll get from it. So this is related to homework, but I'm not going to quite do the same thing that was in there. Now, it generally has to be true when you have a symmetry that the conserved charge associated to that symmetry has to generate the symmetry under commutator, which means that this had better be equal to delta epsilon of x. This is true for any symmetry, but in particular it's true for conformal symmetry. And I want to unpack this a little bit into a word identity. So I'm going to do this in the language of radial quantization. So I need to write this. I need to write out this commutator. Okay, so it's q of epsilon x minus x q of epsilon. And remember, q is the integral of T epsilon. Okay, so in radial quantization, time goes outward. Okay, so if the Q, let's do this one first. Okay, so this is the complex plane, the Z plane. And let's imagine that X is confined to some region, because it'll be easier to draw the pictures then. So let's imagine that X involves like some operators in this region here. Maybe there's like a few operators inserted in this bubble. Okay, so time starts at the origin and flows outward in radial quantization. So the ordering here is that we first act with x, and then we act with q, which means this is supposed to be an origin, not an x. Okay, so we first act with x, and then with q, which means that q should be call this C1. So q of epsilon x is the integral over C1 of epsilon t x. Well, let me write the arguments there because that'll get confusing. Epsilon of z, t of z, x. Integral dz. Okay. Now, for the other one, x q of epsilon, we want to first act with q and then act with x. So that's going to involve the integral over this contour C2 of the same thing.
This is because this thing always produces time-ordered correlation functions. The path integral always gives you a time-ordered correlation function, and that's why the ordering has to do with when they are in time.
Yes, that's right. That's right.
So there should be xt also.
What? Here?
Oh, no, that's fine.
Yeah, this is okay.
Yeah,
In fact, t commutes with x,
yeah.
so.
Yeah.
Okay, so that means that q of epsilon comma x is the difference between, it's the difference between those two q's. Now, if q were truly conserved, that would be 0. But it's not because of those x operators. Okay, so if you remember when we talked about conservation, the difference between these two, you can do Gauss's theorem or whoever's theorem it is that turns this into an integral of the divergence. And so that difference, q comma x, is the integral d2x d mu t mu nu of x epsilon nu of x x.
So is x itself a charge or it's a local operator?
No, x is just some other local operators inserted somewhere.
Okay.
So we can either write it this way, or we can write it as we did over there. So let me write that one also. That one's also useful. And these are delta epsilon of x equal to this, and it's also equal to that contour integral. So this is minus 1 over 2 pi I. I think actually I was missing some 1 over 2 pi's in my definition of the charge. Yeah, I was. Sorry, because t it's 2 pi tzz, so then you have to divide by the 2 pi when you write the charge. So the true expression with all the coefficients in it is this one, integral dz, epsilon of z, t of z x, plus the one with bars. Now, in these expressions, you can just take your integrals to go around x. So in other words, I've taken those contour integrals over there and deformed, when you take the difference, you can deform that to just wrap around the operator x. If x is a local operator, let's say x is just a local operator inserted at a point w, then we can go one step further and write these integrals as residues. Okay, so the final version of the word identity that I'm going to use later is this one, delta epsilon x of ww bar is equal to the residue z near w, epsilon of z, t of z, x of ww bar, plus bars. We're going to use that one to calculate entanglement entropy next week, so that's why I put a box around it. I have too many boxes now. It's like box inflation. Let me work out a quick example of how you use this kind of stuff.
No, this wouldn't have been true in the homework because we weren't doing two dimensions there. Right?
Well, you can't write them as contour integrals, so you don't get this nice residue formula. Some of these equations would have been true, like there's one like this. Well, the first one would have been true with the difference of two things, and this one would have been true. And one way to derive those, I can't remember exactly what the homework questions asked, but one way to derive those delta functions is by demanding this integral to give the right thing. Like this integral has to give the transformation law of x. So if x is a local operator, all contributions have to come from delta functions. So this is a way to derive those delta functions.
But you certainly don't get this residue.
No, you don't get the residue thing in higher dimensions. Okay, so here's an example. Z goes to Z plus A. That's a conformal transformation. So this is translation, but it's also a conformal transformation with epsilon Z equal to the constant A. And therefore, the residue at Z near W of T of Z O of W bar is equal to the transformation with epsilon equals A of, well, the infinitesimal transformation of O of W, comma W bar, And if you take a local operator and you do a constant variation, that's just the derivative. So this is dO of W bar. You can run through the same argument for the dilatation, and that tells you about the residues of Z times T of Z times O of W bar. And it tells you that this has to equal H O. So if you put these two things together, this residue is telling you about the term in this product that goes as 1 over Z minus W. This residue is telling you about the term in the product that goes as 1 over Z minus W squared. Sorry, this should have been, I'm confused, that's, yeah, Z minus W squared. So therefore, putting this together, we get T of Z O of W bar it can maybe have some even more singular terms, but we know that it has a term H O of W over Z minus W squared for the dilatation, and we know that it has a term dO of W over Z minus W for the translation. And then there's stuff that's less singular.
I think that should be HO plus the derivative of O.
Why do you say that?
Because
Because of the 2, I think.
Oh yeah, there's a derivative there. Yeah, thank you.
COP, that's a factor of 2.
What?
No, sorry.
the HO plus part is the derivative.
Yeah. But is this, did I get this one right?
Yeah,
this one is right. Yeah, so if you take those two singularities and you put them together, these are the singular terms. Now, if you had more stuff here, that would correspond to the variation under special conformal transformations. But primaries are annihilated by special conformal transformations. So this stuff here vanishes for primaries. So now we know the singular terms in the OPE for primaries. So we've seen, again, what I was saying in words before, which is that the singular, if you have a current, and this is true in general, if you have a current, something that's conserved, then the singular terms, when that current comes near something, you bring that current near something, the singular terms tell you how that something transforms under the symmetry associated to that current. So this is true in general. All right, we have one more page of CFT for next time, and then on to entropy.